Hello everyone, hope all are doing good. So in the previous session, we discussed about the reactions of di and tricarboxylic acids. Even we discussed the reactions of citric acid as well as the tartaric acid, though it was a small session. So today we shall start with the reactions of some of the important organic compounds such as acid chlorides, amides, acid anhydrides, as well as esters. To start with, let us go with acid chloride. So, as you know that acid chlorides are nothing but they are set of organic compounds which contain a chlorine atom that is attached to an acyl group. I shall repeat. So acid chlorides, they are nothing but organic compounds containing a chlorine atom attached to an acyl group. So you have C double bond O, and to that carbon, a R group is attached, and to the same carbon, Cl group is attached. So instead of OH, if you find chlorine atom attached to the carbon, then it results in the formation of acid chlorides. First, we have hydrolysis of acid chlorides. Hydrolysis in the sense, the reaction or the breaking up of bond in the presence of water, splitting up of the molecule in the presence of water. So here, as an example of acyl chloride, we are taking acetyl chloride, that is CH3, C double bond to Cl, where you have CH3 in place of R, and in place of OH we have Cl. That's a example of acyl chlorides or acid chlorides. So acetyl chloride on hydrolysis yields an acid, that is carboxylic acid, since the halide group will be removed as acid. As I said, if you just remove the Cl and place OH, it becomes your acetic acid, right? So if the same Cl is removed and placed by hydrolysis process, this acetyl chloride gets converted into an acid, and this chloride gets removed as a mineral acid, that is your HCl. You don't have mechanism, so this simple reaction will help. Second, we have the reaction of acetyl chloride with alcohol. So whenever we consider the reaction of acids with alcohol, that mechanism or that process is referred as alcoholysis. Alcoholysis, because you are adding alcohol content to that compound. So here, example, we are taking ethanol chloride. In the sense, if you just replace C2H5 in place of R, it becomes ethanol chloride. Or if you replace CH3 in place of R, it becomes methyl halide or acetyl halide. So ethanol chloride reacts instantly with cold ethanol. So here we are not considering the room temperature ethanol, we are considering the cold ethanol, so that the reaction goes in an instant way. And it's a very exothermic reaction in which a steamy acidic gas is given off, and this gas is nothing but your hydrogen fluid. That's the reason we consider cold ethanol, because you can see even in the presence of cold ethanol, the reaction is exothermic. What if we consider the room temperature ethanol? So that might be highly exothermic. So in order to depress this extremity of the reaction, we do consider cold ethanol. And as a result of the reaction of acetyl chloride or any acid halides or any acid chlorides with alcohol, we do get ethyl ethanoate, which is also referred as ester. You should always remember, whenever any acid reacts with alcohol, ester is always formed as a product. The next reaction, the reaction of acetyl chloride with ammonia. So it is referred as ammonolysis. Again, here we are considering ethanol chloride. So ethanol chloride reacts violently with a cold concentrated solution of ammonia. A white solid product is formed, which is a mixture of ethanamide and ammonium chloride. Since ammonia is involved in this reaction, it's a strong base and you have a acyl halide. So obviously, salt will be produced during this process, that is your ammonium chloride. Hydrogen chloride formed would immediately react with excess ammonia to give ammonium chloride. So you need not worry much about these reactions. You have only general reactions. You need not worry about the mechanism because as per your syllabus, mechanism has not been asked. Sit and practice these equations. Next, we have the reaction of acid chlorides with dialkyl cuprates. The reaction of acid chlorides with lithium dialkyl cuprate, it produces ketones. So this R prime to CuLi is nothing but your lithium dialkyl cuprate. So this R prime to can be any two alkyl groups. So acid chloride in the presence of lithium dialkyl cuprate and hydronium ion. So in the sense, this reaction is taking place in the presence of an acid and the water, which in turn releases this hydronium ion. So I can consider this reaction to be a acidic one. So acid chloride in the presence of or on reacting with lithium dialkyl cuprates in acidic condition results in the formation of ketone. And since one of the R prime from this lithium dialkyl cuprate is being substituted in this acid chloride, the remaining R plus Cu, it may react with water resulting in some other product. Next, the reaction of acid chlorides with Grignard reagent, it produces tertiary alkyl. So you have alpha MgBr, which indicates a Grignard reagent, and this Xs can be any halogen group. Again, this reaction takes place in acidic condition, resulting in the formation of tertiary alcohol. And we know that the Grignard reagents are reproductive. They can be regenerated back at the end of the reaction. So next we have acid anhydrides. So acid anhydrides, they are nothing but a set of organic compounds where you find two acyl groups being bound to same oxygen atom. I shall repeat. Acid anhydrides, again, they are set of organic compounds where you can see two acyl groups are found bound to same oxygen atom. This is your acid anhydride structure. You have two acyl groups, this C double bond OR and C double bond OR, and they are attached to same oxygen atom. So these compounds are referred as acid anhydrides. So first we have hydrolysis of anhydrides. Carboxylic, acid anhydrides, nothing but carboxylic anhydrides. They particularly which have got the low molecular weight on hydrolysis, they result in the formation of carboxylic acid. Here I'm considering only those acid anhydrides which have got low molecular weight. So those with low molecular weight, they end up with the release of 2-carboxylic acid upon hydrolysis. Next, we have a reaction of acid anhydride with alcohol. So here, the example we are taking is acetic anhydride. So it reacts with alcohol to form an ester, and it gives out an acid, that is the carboxylic acid, and this method is considered to be one of the best method for the preparation of esters because it is a bit simpler method and can be carried out at room temperature. And one of the merit of this reaction is that you get carboxylic acid along with ester, where the percentage of ester is dominating and the percentage of carboxylic acid is less, but still we get both the products whenever we made alcohol to react with acetic anhydride. Though this is not involved in your syllabus, I just felt like sharing. So we have cyclic anhydrides, which upon reacting with alcohol, they result in the formation of an structure where you can find two groups. One, you have the acid group, that is the carboxyl group attached to the opened ring, and you have an ester group attached to the opened ring. So the structure is referred as an alkyl hydrogen phthalate. So whenever cyclic anhydrides they undergo reaction with alcohol, they result in the formation of a structure which has both ester as well as an acid as the functional groups. Next, we have the reaction of acid anhydrides with ammonia. So here the reactions between an ethanoic anhydride and ammonia. So the resultant form is your ethanamide. The ethanoic acid produced reacts with excess ammonia to give ammonium ethanoate. It's not necessary. You can simply give a general expression, or you can change the structure of the general equation, where in place of R you can put CH3CH3, so it becomes acetic anhydride, right? And amine remains same. Again, in place of R and R prime, you can keep two alkyl groups, or otherwise you can simply write this general equation, and here you can write, instead of ethanoic anhydride, you can simply write as acid anhydride and ammonia. The amide form is called an amide, okay? And the ethanoic acid produced reacts with excess ammonia to give ammonium ethanoate. So it depends on you whether you want to write a general expression or you want to give any example. Next we have amides. Amides are those organic set of organic compounds where you have NH2 group as a functional group attached to the carbon. First we have reduction of amides. So see here, instead of OH, we have NH2 group as a functional group. So amide reduction is a reaction in organic synthesis where an amide is reduced to either an amine or an aldehyde functional group. So I missed out this example for the formation of aldehyde group. I just got one example where amide upon reduction yields you amine. So you can write any one of the reaction. It's not necessary that you should write both. Any one, that is a reduction of amide to a amine, or reduction of amide to a aldehyde. Next we have hydrolysis of amide. So here we are considering the hydrolysis of amide in two conditions. One is in the presence of a strong acid, that is acidic hydrolysis, and second one is in the presence of a strong base, that is basic hydrolysis or the alkaline hydrolysis. So amides undergo both kind of hydrolysis. So under acid hydrolysis, it results in the formation of a carboxylic acid and ammonium salt is formed. So here you can see I have considered acetamide, which undergoes acid hydrolysis. As I said, here your water and HCl, they result in the formation of hydronium ion, which sets up acidic condition, and upon heating, this amide, it splits up into two products. One is ethanoic acid, that is acetic acid, and ammonium chloride, which is a salt, because you have a nitrogen carrying a plus charge and HCl carrying a negative charge. So this forms ammonium salt. And this is one of the example for a cyclic amide. So you have this ethanamide, or it can be referred as ethan benzamide, because the amide group is attached to a benzene ring, which in the presence of acidic condition results in the formation of benzoic acid, because you have COH group attached to a benzene ring. So you can prefer any one of the example, not necessarily you should write both. It all depends upon the marks. Whichever example you feel comfortable, make sure that you practice those examples. Again, I'm repeating, you need not worry about the mechanism. As per your syllabus, you don't have mechanisms. You have the simple reactions and the products that are formed. Well, next we have the basic hydrolysis. In the presence of a strong base, it results in the formation of carboxylic acid and amine. So this is general equation, and here you have an example. Next we have Hoffman rearrangement. Please do make a note of this, that Hoffman rearrangement, it has a 4-step mechanism. So you have to practice this. This is not a simple reaction. It can be asked for more than 4 marks since it has mechanism. So the Hoffman rearrangement is an organic reaction used to convert a primary amide to a primary amine using a halogen, base, water, and heat. And this reaction is named after its discoverer, August Wilhelm von Hofmann. This is about the mechanism. This is the entire mechanism where an amide is getting converted to a primary amine. So the first step is the reaction begins with deprotonation of the amide by the base to form an anion. Here you can see there's removal of hydrogen atom. Here it is NH2, here it becomes N minus H. So there is a removal of hydrogen as proton of this amide by the base. So this OH minus indicates the base to form an anion. This R double bond O NH minus indicates the base, and which then attacks the halogen to form a N haloamide. I shall repeat the first point. The reaction begins with deprotonation of the amide by the base to form an anion, which then attacks the halogen to form a N haloamide. So first there is deprotonation, that is removal of one hydrogen as a proton from the amide group. Then it results in the formation of an anion, which later gets attacked or which later attacks the halogen, resulting in a formation of N-haloamide. So here you have bromoamide because the bromine is the halogen. Okay. And second point, again a deprotonation process takes place by the base, which again provides an anion that rearranges to give rise a isocyanate. So these two structures are the resonance structures or the rearranging structures. They both are anions which are obtained by the deprotonation by the base, which had resulted in the formation of an anion, and these two anions are rearranging themselves in order to give rise to a intermediate referred as isocyanate. This is your intermediate isocyanate. And this isocyanate is later attacked by water, which after a series of proton transfer results in zwitter ionic intermediate containing an ammonium cation and a carboxylate anion. So this carbamic acid can be considered as a zwitter ion intermediate, which contains here NHR. The charges are missing. This NHR is your ammonium cation and this is your carboxylate anion. If I split this compound, it becomes NHR plus and this becomes COO minus anion. Later this zwitter ion intermediate under thermal conditions or upon heating results in the formation of an amine releasing carbon dioxide, and you can see each steps are set equilibrium with each other, that is it can be reversed back. The entire mechanism can be reversed back. Yeah, here you have the points. The reaction begins with the deprotonation of the amide by the base to form an anion, which then attacks the halogen to form an alloamide. And the second deprotonation by the base provides an anion that rearranges to an isocyanate intermediate and releases a halide anion. The isocyanate is then attacked by water, which after a series of proton transfer results in a zwitter ionic intermediate, that is your carbamic acid, containing an ammonium cation and a carboxylate anion. Under heating conditions, it results in the explosion of carbon dioxide gas and quenching of the ammonium cation to the amine product. So please do practice. You have this Hoffman rearrangement along with the mechanism. Well, next we have esters. Again, esters, they are set of chemical compounds which are derived from an acid, where you can see one of the OH group is being replaced by an acyl or an alkyl group. And if I just simply consider esters, uh, as you've seen in the previous slides, they are derived from a carboxylic acid and an alcohol. Whenever any acid reacts with an alcohol, you can see the esters are formed as a product. So this is your ester where OH is replaced by R, which is your alkyl group. So in organics, so first process we have transesterification. So what is transesterification? In organic chemistry, transesterification is a process of exchanging the organic group R double prime of an ester with the organic group R prime of an alcohol. These reactions are often catalyzed by the addition of an acid or base catalyst. So you can see here the OR prime gets replaced by the H of your alcohol, which results in the formation of an ester. And this is an example. Well, coming to ammonolysis, esters react with ammonia, primary and secondary amines to produce amides and alcohol. Alcohols are produced as byproducts in all the three reactions. The first you have general reaction of ester reacting with ammonia, forming an primary amide. Second, ester reacting with primary amine to give rise to secondary amine. And in the third equation, we have ester reacting with secondary amine to give rise to tertiary amide. And this is with respect to an example where you have I guess it is ethyl acetoester, because you have CH2CH3 and one of the CH3 group here. Next, we have hydrolysis of esters. Esters are neutral compounds, and unlike the acid from which they are formed. In typical reactions, the alkoxide is OR prime group of an ester is replaced by another group. One such reaction is hydrolysis, literally splitting with water, and the hydrolysis of esters is catalyzed by either an acid or a base. Again, under hydrolysis of esters, we have acid hydrolysis as well as the basic hydrolysis. We shall go one by one. So this is acid-catalyzed hydrolysis of ester. Here the ester is heated with a large excess of water containing a strong acid catalyst. Like esterification, the reaction is reversible and doesn't do completion. And here we have an example of butyl acetate reacting with water to form acetic acid and 1-butylone, and you can see the reaction is reversible and doesn't go to completion. You don't get 100% product because the reaction is always reversible. So this is a general reaction where an ester is reacting with water in the acidic conditions, which is in the presence of any acid which produces H+, results in the formation of a carboxylic acid and the alcohol. And this is an example where butyl acetate results in the formation of an acetic acid. Next, we have base-catalyzed or alkaline catalyzed hydrolysis of ester. When a base, such as we know that the strong bases like KOH or NaOH are used to hydrolyze an ester, the products are a carboxylate salt and an alcohol. As a specific example, ethyl acetate and sodium hydroxide react to form sodium acetate and ethanol. Generally, this base-catalyzed hydrolysis of ester is nothing but a method referred as saponification. I hope you people know that what is saponification. It's nothing but the reaction of a base with an ester or any oil contents or protein contents result in the formation of salt of carboxylate. A carboxylate salt is nothing but a soap, right? So this base-catalyzed hydrolysis is nothing but your saponification process. So here you have an ester, a base, results in the formation of an alcohol and a carboxylate salt. So as an example, we have taken ethyl acetate and the base of sodium hydroxide, and you've got sodium acetate, it's nothing but the soap, and ethanol as the other byproduct. Well, with this slide, I'm winding up this unit, that is carboxylic acids and their derivatives. So in the next session, I shall start with tautomerism and enolates. Then we shall go with environmental chemistry. I hope I still remember that I have mailed you the solid state presentations. Once I complete this tautomerism, enolates, and environmental chemistry, I shall go with solid state, where I shall make sure that I'll explain you properly. And after these things, I guess we'll be left with last one more unit, that is phase equilibrium. We shall see how things go. So please do sit and practice, because in this concept you have only reactions and only one mechanism you have got, that is the Hoffman mechanism, which is pretty easy. So please do sit and practice. Don't waste your time. Till then, take care. Bye bye. See you in the next session.